Let's move on to the next speaker. That's Sven Christian from RISE, who will talk about time and frequency transfer over optic fiber optics. Welcome. Thank you.
Thank you. So we are ahead of time, so can I talk for 50 minutes? Good. As said before, my name is Sven Christian Ebenhag. I work as a technical manager and senior scientist for time and frequency at RISE, the Swedish NMI. That is a National Metrology Institute. Karin asked me to talk about fiber and the time and frequency transfer of it. It's not really that easy to do, so bear with me. It will be just a brief overview of what has been done so far. This is the outline of the presentation. So I will start by talking about the clocks and how we calculate and do calculations regarding the clocks. I will talk about fiber connections and the previous performed experiments and which techniques that were used. I will go into the recent experiments in Sweden, and I will also present what we are aiming for in the near future. And I also stole some picture of the internet. I tried to give them all credit, but I maybe missed some. So at the beginning, how long is a second? Does anyone know? No hands in there? Yeah. So from 1967 to present, we have something called the atomic second. It's based on radiation in the Cesium-133 atom, which means that we are counting periods of the electromagnetic radiation locked to an atomic resonant frequency, which also means when the atom changes energy levels, it either radiates or absorbs energy with a specific frequency. So what's that frequency then? Yeah, so that's the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the hyperthin levels of the ground state of Cesium-133. It's easy to count, isn't it? Also, we have had other definitions of the second, which means that the number was chosen, so it should be equal to the previous definition of the second. So we have been talking about clocks, and there are different kind of clocks, from the easiest or the most, the clock with the worst stability. That's in this picture, the rubidium clock. It could give you kind of good holdover for an hour or so. We divide them in commercial ones and into lab ones. So these three here is commercial ones. So we have the Cesium beam tube standards. The 1571 was developed in the 50s or 60s. It has a frequency stability of 10 to 1 parts 10 to minus 12 or down to 13. Then we have the hydrogen masers. In this picture, we have an American one in black and a gray one from Russia. Those are the commercial ones. Then we have these kind of cesium fountains. There are roughly a handful of them across the globe. They have a stability 1 part 10 to minus 14. It isn't enough. When I started to work with this, it was more than enough. But as a society have developed, and we need to have better clocks. So now we're looking into these kind of optical clocks. And as you can see, it's just a lab equipment. In this case, it's an ytterbium optical clock. They run for a week maybe, with 20 persons running around it and pet it. So yeah, it will take a while before we could use it for in robustness use. Yeah, so I promised someone in the audience to present how a cesium beam tube actually works. So up here you have the full setup, the beam tube that you can buy from Microchip. It's an old picture. They were formerly called Symmetricon. It's not that hard. You have the atomic source that is an oven. You propagate the atoms through the selection state. That is, in this case, a magnet. And you pick out the atoms in the right state. You let them propagate a bit more to the trapping cavity. And then you apply a microwave on it to have them to go up in the fully right state. And at the end, we have the last selection magnet, which means that you select out the atoms you don't want to have, and then you have a detector. On the detector, you will have a peak, and when the peak is really high, you know that your microwave source is tuned. And then you try to tune your source into have the highest peak or the most atoms. This picture is from Microchip's fabric manufacturer. They just saw it in half just to show you how it's built up. So this is really cool to have all these clocks in a lab and a bunch of nerds patting them. Yeah. So what do we do with it? So at RISE, as a host of the Swedish National Timescale, UTC-SP, since we were formerly called SP, we have in our possession roughly 24 to 30 clocks, depending on the state at the moment. We always need to have at least 3 to figure out if some of the clocks is performing badly. We measure all these ones, our clocks, with a time interval counter, and we create a group clock. We apply a correction, and then we have the time scale, UTC-SP, the realization. So I saw some previous slides yesterday. You should actually refer to time scale, not to UTC. UTC is a paper clock that you have 30 days after your happening. Yeah, so Bureau of Weight and Measurement in Paris get all measurements from our clocks and also our comparisons with other timing labs across the globe. And then we use GNSS, Global Navigation Satellite Systems, as well as geostationary satellite to compare our clocks to the rest of the world. And all this data go into the correction part. Yeah, so when we talk about time links, we have been talking about fibers. So I would say that fiber is the best way of doing stuff. But Bureau of Weight and Measurements, they really enjoy these GNSS and satellite time links, which means that they actually is running like this. You have a clock at 2 sites. You use the satellite. You send your time. I'll compare your time with a satellite clock from both clock locations, and then you can count out the satellite oscillator and have a direct comparisons between the clock at site 1 and the clock at site 2. As for the moment, it's only 2 or maybe 3 fiber connections that are approved by BIPM for use. Yeah, so this is what BIPM actually are doing every day, and you get your result after a month. They take all the measurements from the commercial atomic clocks with stability better than 10 parts to minus 12. They apply an algorithm for selection and weighting of the clocks, which means if you have an iron maser, it will have a higher weight than a cesium clock. And then you get a shell atomic libre. My French is really bad, so the free atomic time scale. If you apply a steering on that, and that steering comes from these non-commercial clocks, or the cesium fountains and rubidium fountains and so on, you will have the atomic time. But the atomic time will vary against the Earth rotation. So therefore, we have these observatories and the International Earth Rotation Reference System services that apply leap seconds. And then we have the UTC. That is a paper clock that you get hold of 1 month after its real appearance. As I said before, there are commercial ones, and we have lab standards. When I started, the lab standards were really good enough. But what we're aiming for nowadays is this kind of optical clocks. In this case, we look into an energy transition of about 700 terahertz in blue. Since they are optical, we have roughly 10,000 times higher precision. And the only way to compare these kind of clocks is by using optical fibers. They are far from a finished product, so I think it will take 5 or 10 years before we can buy them. Yeah, and also we need to have this frequency stability plot, of course, since we're talking about time. So we have the log scales, instability, and in seconds here on the x-axis. This is 1 day of measurements, 1 month of measurements, and yeah, if you look into this graph, you will be able to decide which kind of oscillator you need for your equipment. The most best commercial clock at the moment is these active hydrogen masers. But depending on what you want to provide and have for a product, you might be able to reach your what you need with the Cesium clock. So that's about clocks. What do we do then? I saw some slides here previously of Sweden, the map, and these are the locations where Netnod have redundant sites. And you saw the systems before, it's built up like this. You have the clock. It's a really neat system. You have 12 timescales. And timescale means that you apply a steering on the clock. And also you have the NTP, PTP, and so on, and whatever you would like to have of kind of signals like 1 PPS, a frequency, and so on. And then they get traceability from the national timescales through GNSS. So far, we don't have any fiber connections between RISE and Netnod sites. Maybe it's there one in Stockholm, but yeah, it's just for testing purposes. Yeah, so if you need traceable time, you should go to Netnod. They have a really good time. So when we do time transfer, we need to do it two-way to be able to have a good accuracy and so on. And also it presumes that you have bidirectional symmetry of the delays. And that's not always the case. When you do it in free space with light or a microwave, it's the case. The delay for both directions is equal. It's the same for a single fiber, of course. But when you have dual fibers, that's not the case, even if it's uninterrupted. It might be due to length or refractive index or temperature variations and so on. So we preferably always have one single fiber. And even if you put in this kind of switching routing, it's not a good idea for time and frequency transfer if you want to have it in a good way. Also, we know that fiber is one of the best temperature sensors on the world, on Earth. We know that the fiber delay varies approximately 30 picoseconds per nanometer kilometer degrees Celsius. And also, if you bury it in the ground, it might vary up to plus minus 10 degrees over the year. We have proven this. So in red here, we have 560 kilometers of fiber hanging along the power grid. And you can see these daily variations and also monthly variations. At the same time, we had a fiber on the seabed of the Baltic Sea, and you can see it's much more stable. It's a nanosecond scale up here. These jumps were due to change of amplifiers. So we talk about time transfer, we talk about time delay transfer, we talk about frequency transfer. So time transfer is when the time data is transmitted and the receiver can set its own clock to the link. Time delay transfer is when the link delay is monitored and transmitted to the receiver, and you can use it to compare your clock with the link data. And then frequency transfer is more or less the same. The frequency transmitted and receiver can compare is oscillator using the link. So now you have the background. We will now go into different kind of systems that have previously been tested and up and running. And the first system I will present is SATRE via fiber. So SATRE stands for Satellite Time and Ranging Equipment. We use it for these geostationary systems. So actually it's just a modem. And we replace the transceivers, the satellite transceivers, with optoelectronics. And if you do it for 73 kilometers, you will have an uncertainty below 100 picoseconds. So that's fairly good still. It's a single fiber, and these modems are really expensive. We also played around with a stage protocol, synchronous digital hierarchy. It might be of use on some locations, but not near the networks I'm in. So when we played around with it, we used STM64, and we timestamped the header, which means that we got out 8 kilohertz signal. We needed to know and estimate the distance within 10 kilometers to know which timestamps that belong to each other. And also we needed to have these slave clocks since it's an asynchronous link. It worked really good. We compared it with GNSS, Common View. So we don't really know which system was the best, but it's a redundant system to GNSS. Still, it's obsolete nowadays. Some other groups in the US and also in Japan played around with SDH. They set a bit in the header and timestamped it. They also put in IRIG-B signals in the payload. Worked fairly well as well, but still, it's of no use. And as you can see, this was a long time ago. Chestnut in Czech Republic put the 1 PPS on the RF carrier. They built their own equipment. They had equal as good results as the GNSS. Still, it's on-off keying. They demonstrated it for duplex fiber. It's worked really good, and they had it in a DWM network. The Chinese group had another idea. So they used the same wavelength, but they only had one pulse at the time, so they sent a pulse to the receiver and then sent it back, which means they only have one pulse present in the fiber. That was to avoid interference from radio scattering. Yeah, it also worked well, but still, it's really hard in Sweden to, and expensive, I would say, to buy a single fiber to be able to produce this. The Polish research group had another idea. So they had a variable electrical delay in each the transmitter and receiver, and they were compensating on each side for the delay variation. It worked really good. Still, it was developed for a single fiber or simplex fiber. We tried it out in Sunet for long distances. They were really mad since I didn't tell them for which kind of distance that I would use it for. So I used it for 300 kilometers or so. It was only developed for 10 kilometers. Still, it worked fairly good. Yeah. So this is a commercial product that you're able to buy. I don't know the price, though. In the Netherlands, they had a really good clock laser. They just transmitted it for different kind of distances, like 10 to 100 kilometers, send it back, and performed link characterization of it. Yeah, it performed fairly well. So if you look into here, 2 parts to the minus 15 for 5.5 hours. It's not really true since you are missing the error bars, so the error bars might be big, but still it's a good result. You're able to transmit an H measure or something. The Swedish company Net Insight, and maybe they hang me later on since it's an old slide. It's an old system. So they performed this 1,200 kilometer link over different kind of mix of systems. They have asymmetric jumps in the WAN area, and they use an Nimbra, so they had in GPS, and the output time varied roughly 1.5 microseconds for a longer time period. And then they gave me this kind of graph, and as you can see, it's only very well, plus minus 160 nanoseconds per day. Nowadays, they have a better system, and I don't have that new data, so talk to them if you need or want some new data. Also in the Netherlands, they started the work with using the surveillance channel. So they performed it in the 1600 nanometer band. They took out the wavelength they needed, and also they had these bidirectional amplifiers, which means that the system will be really expensive. It's working really good, but then you need to have a lot of jumps in between. The one I really like, since we have good lasers, if these optical frequency transfers, which means that you're sending light through an AOM to a reflecting mirror, you get the light out, and also you get some part of it back. You detect it, and then you steer the AOM to compensate for variations, which means that it will be really stable. So the Germans performed that for 1,840 kilometers. And also they did it in a ring, so as you can see, they have the sending and receiving site just 1 meter apart, so I don't really know how you should use it in the real world, but they performed really good. They reached 1 part to minus 20 for again kind of long time period, so that's really good. So they wanted to test this in a real network, so they talked to the French research group that also developing optical clocks, and they set up a link of about 1,400 kilometers, and the geographical distance is just 700 kilometers. They have an uncertainty of 5 × 10⁻17, which is good, and you are able to compare optical clocks with it. Then we have the optical comb group in NIST at Boulder. They have really good optical clocks. They build fiber optical combs, and they want to use them for something. So they set up a mirror on a mountain, and they shot out pulse train and received it. And yeah, if there weren't any air turbulence, they could actually have deviations below 1 femtosecond for a synchronized system. So that's really, really, really good. But just for a short distance of 4 kilometers in a folded path. So then we have limitations in duplex fibers. We have unknown asymmetries that limits our time transfer performance. We need to identify the constant asymmetries through calibration or alternative techniques. And also we have these variations that we need to estimate. It's not really that easy to estimate every time we do these experiments, but we try to. Also, if you do simplex fiber, you have some limitations. The maximum distance It's limited by attenuation, since you're not able to attenuate or amplify the much you like to do. And also, in some part, you actually will have some duplex sections, and that need to be climate controlled. And also, all path lengths should be identical. So who needs this kind of precise time and frequency? These are the areas that Clonets identified. So it's transport, navigation, power grids, finance, defense, security, science, telecom, more or less everyone. I think Fredrik told us that no one wants to pay for it, though. That's the hard part. So thank you, Fredrik. Yeah, so I also stole this picture from them. Depending on which kind of accuracy you would like to have, you have NTP in millisecond, down to microseconds. Now you have PTP, GNSS, White Rabbit here, and between microseconds and to low nanoseconds. And if you want to have better and compare optical clocks, you need to do optical time transfer. Yeah, just to give you an idea of the TRR level and the distance. It's a lot of work ongoing on these fiber connections. Everyone wants to have redundancy, and as I said before, they are not there. They don't have this kind of robust thickness in distributing the timescales and having clocks across the country. But they started to do that. So they have fiber links in Czech Republic, in Italy, of course in Sunet. This is in UK, Finland, Germany, France, of course, up to UK, the Netherlands, and Poland. Poland actually have one of the first approved fiber connections of BIPM. It's an old slide. This connection is not in use anymore. I would like to have it in use just to test it out, but yeah, we will see, maybe later on. So, some of you know about White Rabbit. That is a profile in PTP. So we tested it out in Sunet between RISE in Borås and Chalmers Onsala, the Space Observatory. And for you who's not from Sweden, these are the sites. Just to test out and see how it's performing. And yeah, I will not bore you with graphs. So it performs really well. It's better than GNSS anyway. So if you're able to use White Rabbit, do it. It's working well. We set up this kind of implementation. We used our masers. We used also the time scale. We compared it with GNSS, and we had Sunet in between. Yeah, just a simple setup. Then we have Netnod and Ragnar, who performed White Rabbit also in the surveillance channel with 8 intermediate jumps. It's a distance of 440 kilometers, used BiDi. They had asymmetries in fibers, but they performed calibrations. And since it's Sunet, it's in power grid fibers. Yeah, so they used the surveillance channel, so around 1610 nanometers. Just show me some picture or results of it. So yeah, it's varying about 2 nanoseconds, and it might be better if we do some better calculations of the GNSS connection that is compared to. So it's really good. So what do we want to do in the future then? We know that Sunet is a coherent system. We know that no one in the timing community are building coherent transceivers. So we looked into Michael Mazur, previously at Chalmers University, now at the Nokia Bell Labs. He performed this kind of stunt a couple of months ago, doing environmental measurements for a distance of 524 kilometers in Sunet. Really impressive. but we are aiming of using this kind of platform and make it work for time and frequency, to be able to actually distribute within SUNET, and then Netnod will be able to distribute time and frequency even better than now. So what we actually propose is a project that shall deliver a technical solution, a comprehensive applicable algorithm, adapted hardware, and knowledge on how to work to compensate for asymmetric uncertainties that arise during wavelength-based coherent transmissions in fiber. And this final line I really like. After completion of project, it should be possible to work in a real network. That's not very common in the research community. So what's our aim then? It should be able to work in SUNET-C, for instance. We need to be able to change the wavelength. It should also be able to operate with duplex fibers with the best possible uncertainty. We should be able to track polarization and compensate for it. It should be able to use for time and frequency transmission independent of protocol. We should actually define it so it can work with intermediate clocks. And the two last bullet points here, the stability must be better than GNSS. But even if it's not, it could be of use as redundancy to GNSS. And we should be able to actually do transmission of hydrogen masers from those locations that we have that. So thank you for your attention.
Any questions? Sten Ling.
Okay, let's jump right into it. So I guess these last couple of slides were showing mostly the very high accuracy distribution, but just in general using PTP over like a commercial IP network or a packet network, what kind of accuracy do you see today?
So depending on if you do calibration, you can receive near a nanosecond with both White Rabbit and PTP if you have a dedicated connection. If you distribute it and route it, microsecond. It's still, I think we should look into it like this. We need a microsecond today, but we need to maybe a nanosecond in 10 years. So we need to be ahead of, the researchers need to be ahead of you in the real world.
For those distances, for instance, Gothenburg to Karlstad, do you need to be optical all the way, or can you do an OAO in the middle to, or does that destroy the signal too much? Optical, electrical, optical conversion.
That conversion is not good in any way. It will add a lot of noise, and you will actually disturb our frequency transmission. So we need to be fully optical the whole way.
Okay.
And if you do optical, electrical, optical, you don't really know that you have a constant delay within that equipment. It varies with temperature and so on.
But that could be had in an oven where you have a constant temperature, such things. It's possible to compensate for that as well. But
of course, everything is possible to compensate for. It's really expensive, though.
Yeah. But then, what is the longest distance? You had some example here, but
we have done 1,100 kilometers.
1,100. Okay, thanks.
So it's possible to do.
Thank you, Patrick Feldström, Netnod. The presentation you saw by Sven Christian was interesting, right? Really cool thing. We do cool things at Netnod. We have a position open. Just apply for it. Thank you.
More questions? I have a question. In the news a couple of weeks ago, it was like a second on the moon is shorter than the second on the Earth due to Albert Einstein and stuff like that. Is RISE or BIPM involved in that, or is it just the space agencies that research in that area, how to handle time on the moon?
RISE is not into it in neither our BIPM, but NASA is into it. They work closely with NIST in the US as well as USNO, so they keep track of it.
Okay. Thank you.
Thank you.
Really interesting.